the consistent theme we're discovering in chemistry, that everything is about random bumps between molecules. And when they bump randomly into each other, a lot of different things can happen in terms of knocking different parts of the molecules off of each other and bonding to different things. And this includes pure water, which for the most part, one would think is a pretty stable substance, and it really is. But it turns out, let's say if we start with 2 water molecules, and when I put a 2 here in any of these, this is going to turn into an equilibrium equation. It could represent 2 molecules. It could represent 2 moles of molecules. What matters is just the ratios in these equations, and I think you know that. But let me just draw 2 for an example. So let's say I have the oxygen end. Let's say I have another oxygen here. They both are attached to some hydrogens. They're sharing electrons with some hydrogens here. And we know that oxygen is a lot more electronegative than hydrogen, so it hogs all the electrons. And what that creates is a partial positive charge at the hydrogen side of the water molecule. They're almost naked protons being attached to the water molecule. So this is positive here. And then the oxygen sides have a partial negative charge because they're hogging all the electrons. And this bond between the negative side of the oxygen molecules and the positive side of another oxygen molecule, this is called a hydrogen bond. And this is what keeps water together and what keeps it, definitely in its liquid or solid states. In its solid states, these bonds become they only stay together in some lattice structure. In a liquid state, they can kind of break and form new ones, but they keep them close to each other, rubbing against each other. Now, it turns out if you just have exactly the right set of circumstances, that if one oxygen, let's say this, this isn't the exact set of circumstances, but I think you can imagine if this moved just exactly close enough, it had enough kinetic energy to move right past this one, there's some probability, and I'll draw an equilibrium reaction here because that is what we are dealing with. The equilibrium reaction. There's some probability that this hydrogen right here gets stuck to this guy. He gets so close and maybe this guy bounces in some other weird way that we get left with, let me draw the same 2 characters, 2 oxygens. Actually, let me draw the second guy. Let's say that he just somehow passed the other guy. So he had some movement. Right, let's say he moved in that direction. That's, this is obviously not scientific, but it gives you a narrative around what could happen. So this is this guy's hydrogen protons. And this was attracted to this oxygen side. And if just under the right circumstances, remember, everything here is probabilistic. There's always a probability of almost anything happening. This guy can get attached to this electron, to the negative side of this water molecule, or the water side. And then this guy is only left with 1 hydrogen right here. And then this molecule as a whole, this is OH, hydroxide, and it has a minus charge, right? Because now water was a neutral molecule. You had just as many protons and electrons. Now we have 1 less proton than electron. So in this case, you just the hydrogen nucleus itself, which is just a proton, because we learned that hydrogen doesn't have any neutrons in its normal form. This is essentially a proton when we draw hydrogen. It gets bumped off or scraped off and ends up on this water molecule. So this guy lost a proton, has the same number of electrons, so he now has a negative charge. This guy has the same number of electrons, but now he's got an extra proton, so he has a positive charge. So this is H3O. With a positive charge. And this little version right here, where you get a water molecule and it somehow gains an extra hydrogen proton or hydrogen atom, this is called hydronium. Hydronium. And this process where water can kind of spontaneously, and I'm not saying that water will, a whole glass of water, this is going to happen. It's actually happening to a very small number of molecules. That if you view this as an equilibrium reaction, when you have 2 waters, this is much more, the reaction is much more weighted in the leftward direction. But this can happen, and that's what the whole point of this is to think about. But this process is called autoionization, because you just have water by itself, and just by some random circumstances of some molecules bumping into each other just right, some subset of the water will ionize like this, where one part will lose a proton and the other part will gain one. So this is autoionization. Let me write that down. Autoionization. And of course, this is an equilibrium reaction, so now these guys might go bump into two other things and become water again, or maybe they'll bump into each other again and they'll become water. So it goes back and forth. So there's some equilibrium concentration of this. And let me write it as a proper equilibrium reaction. So you could have two, maybe moles of water molecules. They are in equilibrium with H3O positive, and all of these are in an aqueous solution, and that's a bit of a redundancy because aqueous solution means that you're dissolved in water. So of course water is dissolved in water, but then H3O dissolved in water. So all around here you have water molecules. This isn't an isolation. You have gazillions of water molecules all around, plus OH minus, aqueous. Now, sometimes you will see this exact reaction written as, you'll see that exact reaction written as this. And it's important that you realize it's the same thing. H2O in equilibrium with just one hydrogen ion popping off. Everything's in an aqueous solution. Let me write that down. Everything is being dissolved in water. Aqueous solution plus OH minus in an aqueous solution. And these are this equation right here, this right here, and what I wrote at the top. And let me cut and paste this so you can see them at the same time. So let me copy, go down here, and paste this. These are essentially equivalent, although the second equation right here describes what exactly happens. So the first equation is creating a picture that you have one water molecule, and there's some small probability that one of its hydrogens just pop off, and you're just left with a hydrogen and then a hydroxide, which is just an oxygen and a hydrogen atom together. But the reality is that these hydrogen protons, they don't exist in water on their own. Whenever they are in water in an aqueous solution, they essentially get a ride with another water molecule, and that's what happens here with the hydronium ion. But the whole reason why I'm going into this whole discussion of the autoionization of water is because people really care about the concentration of, depending on how I view it, hydrogen atoms, hydrogen protons in a solution, or you could say hydronium protons in a solution. The concentration of these two things are going to be the same, right? Because all of these really are riding on another water molecule and becoming hydronium. So how do you measure this? Or a better question is, what is the equilibrium of this reaction? So it turns out that in just regular water, the concentration, and maybe I'll switch to this one, the concentration of, this is in regular water at 25 degrees Celsius. Let me write that down. 25 degrees Celsius, which is roughly room temperature. The concentration, which is with pure water, the concentration of pure water, in pure water, the concentration of hydrogen ions, and we could also say that that's the concentration of hydronium ions, or cations, because they're positive, it equals 10 to the minus 7th molar. Right? So for every 1 liter of water, you have 10 to the minus 7th moles of hydronium ions, which is still a pretty good number because it's 10 to the minus 7 moles. So it's 10 to the minus 7 times Avogadro's number. So let me just do that. So it's 10 to the minus 7 moles per liter of water, which is the same thing as 10 to the minus 7 times, a mole is just a number, 6.022 times 10 to the 23. So you do the math here, you still end up with what? 60 times 10 to the 16th power molecules. So you still have a large number of molecules. It's just a small fraction of the total number of molecules are actually these hydrogen or these hydronium ions. And it turns out that your concentration of hydroxides is also, so your concentration of hydroxides is also 10 to the minus 7th molars. So if we know that, we can now actually figure out the equilibrium constant for this autoionization of water. We can figure out the equilibrium constant. So let's do that. And we'll do it with the first one. So let's say you have, I'll switch colors, H2O in an aqueous solution. It's in equilibrium with hydrogen ions in an aqueous solution, but we know in reality they've gotten rides with other water ions, with the other water molecules, not ions. They turn them into hydronium ions, plus hydroxide molecule. The equilibrium for this reaction, the equilibrium constant, we'll call it for the K sub W for water, it equals the concentration of the products of hydrogen ions times the concentration of the hydroxide ions. Now, in a normal situation, we would divide it by the concentration of the products, but of the reactants. But in this case, and we learned this before, the reactants are what the solvent is. We are in water, so we won't include this. And if you want the intuition behind that, remember this whole thing comes out from the probability of this is the probability of the backwards reaction happening is related to the concentrations of these two things multiplied by each other, and the probability of the forward reaction happening is related to the probability of finding two of the product of the reactant molecules in one space, and you're always going to find these molecules in some place. So it's just going to be a constant probability that some water spontaneously turns into these two products. So whenever you have a reaction like this equilibrium reaction, and the one side is essentially just a solution, you just don't include it. So the equilibrium, or you could just think of it as a 1 down here. So the equilibrium constant of this autoionization water is right there, and I just gave you what the numbers were at room temperature. So the equilibrium constant is equal to the concentration of hydrogen is 10 to the minus 7 plus, times the concentration of hydroxide is also 10 to the minus 7. So it equals 10 to the minus 14th power. Now, and that's a good thing to memorize, the equilibrium constant of the autoionization of water. And all of this is going to, just so you know, this is all going to lead into acids, because essentially people care a whole bunch about what this concentration ends up being. And we're going to touch on that in a little bit in this video. Now, it turns out that people in chemistry, they for whatever reason, they don't like talking in these terms. They don't like saying 10 to the minus 14th power. So what they do is they take the negative log of things, negative log base 10. And if logs are intimidating to you, review the videos on logarithms. So what they do is they take the minus log of both sides, minus log. And when someone just writes log without a number, you can assume it's base 10. But they take the minus log of the equilibrium constant. The minus log base 10 of 10 to the minus 14 is equal to, well, 10 to what power is 10 to the minus 14? Well, it's minus 14, right? And then you have that minus in front. You have this minus, and then the log part is just minus 14, is minus 14. And so the minus log of the equilibrium constant of water is equal to 14. And this idea right here, this is called the pKw. pK. Let me put the P in a different color just so you see where it's pKw. But all P means, whenever you see it in chemistry, just means minus log base 10. Minus log base 10. And there's some debate as to what P stands for. I kind of think of it as power, although it's a minus log, it's an exponent, but whatever. It means you're taking the minus log of something. And what it does is it's just a kind of a way to get out of the exponent world, although I think it's nicer to stay in the exponent world because you really know what you're talking about, into some nice clean number like 14. So when someone says that the pKw is 14, all they're saying is that the equilibrium constant, which is just this part right here, is 10 to the minus 14. Now, the same convention is used on the hydrogen concentration. And there's a lot of the next few videos are all going to revolve around the hydrogen concentration in water, essentially. We'll talk a little bit about what happens when you're outside of water. Now, the hydrogen concentration in water at room temperature, I've told you, has been determined to be 10 to the minus 7 molars. People aren't happy just with that, so what they want to do is do the same thing. They want to take the minus log of both sides, and they define, so they say the pH, and you've probably heard the word pH. It's on a lot of cosmetics, pH balance. Now you know what it means. They're really just saying that we have the right number of hydrogen ions in our lotion or our perfume or whatever we're trying to sell you. So the pH is equal to the minus log of the hydrogen ion concentration, which is equal to the minus log, remember it's just base 10 if I don't specify otherwise, of 10 to the minus 7, which is equal to, well, the 10 to what power is 10 to the minus 7? This is equal to minus 7. Then we have the minus outside. So then this becomes 7. Now, you can do that same exercise for the pOH. pOH, the concentration of hydroxide ions. Well, it's the negative log of the hydroxide concentration. The hydroxide concentration we saw was the same concentration as the water concentration. Oh, no, I didn't write it there. Where did I write it? Right there. 10 to the minus 7th molar. So water has the same number of hydroxides and hydrogen ions. And that's because its water is just dissociating into the two of them. But of course, this is equal to minus 7, right? Log based, this number right here is 10 to the minus 7. So it equals 7. So the pH and the pOH of water is both equal to 7. Now, in the next few videos, we're going to start covering the notion of acids and bases. And it turns out that an acid is just something that increases the hydrogen concentration. Well, that's one version of acids. We'll talk about other broader definitions. But it's called the areneous acid, which we'll talk about in the next video. But if something is making the hydrogen concentration go up, if we put something in water that makes that go up, what's that going to do to the pH? Well, if this number right here goes up, then the log of that number is going to go up. But then the minus log of that number, so let's say, for example, 10 to the minus 7, that's all good. But let's say we take it from 10 to the minus 7. So at 10 to minus 7, that's kind of just neutral water doing nothing. We have a pH. pH is 7. We just figured out this calculation. This is where the hydrogen concentration is equal to 10 to the minus 7. Now let's say we were to do something to the water where the hydrogen concentration were to increase. So we add hydrogen. We add concentration of hydrogen to, let's say, 10 to the minus 3. This is obviously a much higher concentration of hydrogen than that. So the hydrogen concentration is now 10 to the minus 3. What's our new pH? So the new pH is going to be equal to the minus log base 10 of 10 to the minus 3. That's equal to that minus there. 10 to the minus 3 power is equal to 10 to the minus 3. So it's minus 3. So this becomes plus. So now our pH is equal to 3. So the big takeaway from this is we care about the hydrogen concentration. When something increases the hydrogen concentration, that is considered an acid. And that when you increase the hydrogen concentration, when you put an acid into an aqueous solution, you are lowering the pH. So the lower the pH, the more acidic you have, or the higher concentration of hydroxide ion, of hydrogen protons you have. And we'll talk in the next video about the opposite of that, which is basic things. And bases increase the concentration of hydroxide. Anyway, see you in the next video.